One of the most significant drawbacks of using the Erdos-Renyi random graph model is the fact that its degree distribution is not very representative of any real network. The configuration model is you can kind of think of it as a variation on the Erdos-Renyi random network model that will exactly mimic a given degree distribution. And in particular, it's going to exactly mimic the degree sequence because that's exactly what the configuration model takes in is the degree sequence itself. And so it's going to produce a network that is randomized, but that it preserves the exact same degree sequence. So the configuration model starts with specifying the degree sequence. This is a list of n numbers that represent the degrees of all the nodes in the network. In the second step, we add all n of those nodes into our network, and then we give each of the nodes essentially stubs of edges that represent their required degree. So in this example, there's one node that has degree 4, there's 2 nodes that have degree 3, and 3 nodes that have degree 2. And so these little stubs of edges indicate the degree that's being required of that node. And so they're not complete edges because they don't actually connect with anything yet. And so it's in the third step that then we're going to uniformly randomly pick 2 edges and connect them. So we may pick this edge and we may pick this edge, and that means that we'll be connected together. We could also pick this edge and then also pick this edge, which would give us a self loop. And so that's one of the things that we're going to talk about. Notice that we obviously need to have an even number of stubs in order to make sure that we can connect all of the stubs to other stubs. And so this term, this is given the term graphical. So the degree sequence needs to be graphical so it can actually be realized as a network. And so you'll notice that this method of creating the graph is somewhat similar to the ER approach to create a random model. And so it's that kind of random characteristic that preserves some of the analytic tractability, which allows us to specify some of the properties of networks that are generated by this particular algorithm. So in particular, one thing we're going to take a look at is what is the prevalence of self-edges in a configuration model network. And so because we've used this random approach, we can actually specify that, and then we can talk about the asymptotic nature of those statistics. So one of the most fundamental properties is simply just what is the probability that any 2 vertices are connected. So if we have a node I and a node J that have degree Ki and degree Kj, and these lines sticking out of I and J are supposed to represent the stubs. Then the probability that we're going to connect means that we're going to grab one of the stubs from I and one of the stubs from J. And so we can kind of think about starting from node I, and so that means that gives us Ki tries at connecting to Kj. And each of those tries, we're going to be selecting any of the stubs that are on J. So we have Kj options of stubs out of the rest of the edges. So we're 2m minus 1. The one edge is the one that we're actually picking. So the one edge is this one, and we can connect to all of the others. Because remember, anything is fair game. We could have other nodes over here that have edges that we might connect to, that we might select, and we may even select some of the edges that are on I as well. So that means that we have there are Kj options that are connected to J out of the rest of the 2m minus 1 possible stubs. So if we multiply this out and we take an approximation here, we essentially drop this minus 1 and just say that it's 2m, then as long as m is relatively large, so the number of edges is relatively large compared to 1, then we can estimate the probability as just the product of Ki over Kj, Ki times Kj over 2m. And so this is actually something we'll compute several times in the course of the class. But in this particular, this is the first time we're seeing it. So that's the probability to connect any 2 nodes. And so now we're interested in understanding what are the prevalence of self-edges and multi-edges. So essentially 2 edges between the same pair of nodes, or a single edge between the same node. So let's answer the multi-edge question. So this is, what is the probability of having 2 edges between a pair of nodes? So that means that we connect I and j, and so this is the probability that we just computed, Pij, up here. And then essentially we've removed one edge from I and one edge from j because of this edge. And so the next probability for connecting the same pair ij is given by this, where we just reduce the degree of each one of them. And again, as long as m is sufficiently large, then this approximation still holds. And so now we're interested in not just between a specific pair ij, but between all possible pairs ij. And so for that reason, we're going to sum up over all possible I and j. And remember, this is going to double count. So this is going to count when I is equal to 1 and j is equal to 2. And it's also going to count when I is equal to 2 and j is equal to 1. And so that represents the same edge. And so for that reason, we have this 1/2. So the inside, we're going to sum up the same product, the product of these two terms here. And now we're just going to do a little bit of reconfiguration in order to present this in a different light. So we're going to denote by these angle bracket k. This is going to represent the average degree. So k we often use to denote degree. So the average degree is just the sum over all the degrees of the nodes divided by the number of nodes. So that's one way to write the average degree. And this is actually also equal to 2m over n for an undirected network. And so we're going to use this fact to replace this 2m with n times k, this angle bracket k, n times the average degree. And so we have 2 copies of that because we have this square up here. So we're going to get 2 copies of both of these. This 1/2 still sticks around, and that's why we have this 2 here. What's left is 2 terms that are essentially identical. What we've done is we've brought all of the ki terms together and all of the kj terms together. These 2 things are going to be multiplied, but effectively they're the same sum. And so if we look at this sum, we multiply this out, we actually get ki squared minus ki. And what we're going to do is we're going to define, and this is using maybe some more advanced probability, is this is the second moment of the degree. And so if this is the average of the degree distribution, this is the second moment of the degree distribution, and that's the same as summing up over all of the nodes ki squared and then dividing by n. And so if we define this like this, then we can obviously use this sum here to talk about this sum, and we can use this sum here to replace this sum here. And so the only things that are left are these n, 1 over n terms, which cancel with these 1 over n squareds here, because they turn into, we multiply this n over to the other side. So that's actually what we're sticking in, taking this over here, and then we're plugging that in, and so those n terms cancel this n squared. And that leaves us with then this term, the second moment minus the average degree over the average degree, and that all squared. And so this maybe doesn't mean a whole lot to you right now. It's interesting. This maybe we could have some sense on. It's the average degree of the graph. This second moment is a little bit maybe less tangible, but we'll quote a result that's going to help us use this to show that the presence of self-edges and multi-edges are diminishingly small as the network grows. So now let's tackle self-edges. So in self-edges, this means that we're going to select from the edges, the stubs of a particular node. So in this case, node I, we're going to select all possible pairs. So it's all the different ways that we could connect I to itself. And we're going to divide by the complete 2m edges. And so we just rewrite what ki choose 2 is and simplify that down to this expression. And now we're going to sum that up over all possible nodes I. And so that's what we're doing here. And again, we're going to reuse the definitions from before for the second moment and the average degree to see that the prevalence of self-edges is represented by this quantity. And so now this is the result that we're going to quote and not really prove because it's a little bit beyond us in this class. But it says that if the second moment of the degree distribution is constant or finite, which in most practical cases we end up seeing, that the quantities of self-edges and multi-edges is fixed. And if we get bigger and bigger graphs in terms of number of nodes, these go off to 0. So they get smaller and smaller. Their quantities as a fraction of the number of nodes get smaller and smaller. And so that means that overall the configuration model generates relatively few self-edges and multi-edges, and so we don't tend to have to worry about them when we make these graphs. So one of the last tractable questions that we're gonna talk about is, and this feeds into the notion of the friendship paradox in the text, which is what is the expected number of neighbors that we think our neighbors have? All right, so we have to say that. Let me say that one more time. Is that essentially your neighbors? You're interested in understanding how many neighbors your neighbors have. So how many connections your direct neighbors have. And so we can tackle that in a very similar way. So in this case, we're going to first quantify here. So that if a node has degree k, then this is the likelihood that any of my edges will end at the node k. So if it already has degree k, then I'm interested in quantifying what's the probability that any end of an edge is actually going to end at that. So that's just k over essentially 2m. And that's the simplification we're going to make here. And then what we're going to do is we're going to multiply that by the number of nodes with degree k. And so the number of nodes with degree k is simply just the probability degree distribution at k multiplied by the total number of nodes. And so that's going to tell me what the probability of an edge attaching to any vertex with degree k. And then what I'm going to do is I'm going to then sum that up over neighbors. And so we're going to make the simplification that we did before, substituting in for m, this n times k term. The n's cancel, and we're left with this expression, and that is the probability that a neighbor has degree k. So then the average degree of a neighbor is then we sum over all possible degrees, the degree of the node, so how many neighbors, times the probability that a neighbor has degree k. And so that yields us with this expression for the expected number of neighbors that we think a neighbor will have. And we're going to use that in the friendship paradox to show that that is different than what is perceived as your average degree, which in general is just this. So in general, your neighbors look like they have more connections than you think you do. And that's the friendship paradox.